data and AI community for giving me the opportunity to speak in this monthly coffee. I think there will be from Valencia more tech talks during the year. So let's see. This is Jesus Serna, service unit leader in Valencia. My ambition is to understand the fundamentals of AI and to work deeper into the areas that could add the most value to my career, to my role and earning. And yes, well, the basic idea of AI is to be more efficient and to work more intelligently. We must highlight the importance of using AI the most ethical and responsible way. No, so in this case, I'm going to present a project that I developed for my master's degree. And as we do at Ernie MedTech projects, this one also uses the technology to improve our health and protect our health. No. Okay. So the agenda shows the project workflow at the end. We must understand. The first point is that we have to understand the project, the problem, to describe the data set, to do the exploratory data analysis, then to decide which models to use and train them. And point 5 would be to evaluate them, to make predictions, and then we get the conclusions of the best model for this problem. And normally also we set the path for improvements and opportunities. So at the end we will see if you have any question and answer. So well, do you know Kaggle? Have you heard about Kaggle? The web page is one of the world's largest communities to do competitions in data and for data scientists and machine learning engineers. So this is the source of this data set that I will use. I used already in this project about diabetes. And you can join Kaggle in any competition about lots of topics, and it's very, very interesting for improving your skills. So you see the workflow. Initial analysis, then explore your data set, define the objectives, do this EDA, do a pre-processing. We will see some of the features that we do in this step. The modeling, the training, cross-validation, and finally you can parameterize with hyperparameters your model to work even better. It's a regular workflow in machine learning. This project is about machine learning for sure, and it's also about detecting diabetes. Just some lines about diabetes. You will probably be familiar with diabetes issues and how important it is to improve their lives and how especially to those who deal with it. And this slide shows with gross numbers, well, the affected population in the world, no, the trends, the importance to improve the diagnosis process, even the economical impact. So yeah, probably these numbers already show the dimension, no, of what we want to improve. At the end, the problem is this one: to develop a model capable of predicting if you can develop diabetes or not. The type of problem is then classification, whether you will have diabetes or not. So it's a classification problem, and then is. Do you have any questions?
Va fer fred, va ploure molt i va dir, pringao, t'has cregut.
Estic escoltant a Javier i tenim ara parlem valencià. This is a classification model, whether you have diagnosis or not. And then it's supervised classification because we have a data set with the target value that is you have diabetes or you don't have. So it's already tagged the problem. So it's a supervised classification. We will use classification models. Yeah, for sure, the relevance is has lots of relevance as we saw in terms of diabetes improvements, and of course this is supporting any medical decision and so on. This is not a final tool that you can use for fixing problems. No, it's always a tool to help. This important note. So what is the data set that we use for this problem? We have 700,000 lines. There are 700,000 patients with 24 variables, features, or columns, no, of the database. Is at the end, a data set is a database with a big table. No, 24 variables that are integers, strings, decimals, and then one variable that is going to be the target value. So yes or no. The patient has diabetes, yes or no. So 24 variables and one column that is explaining that the target value. So we will see how we are going to work with this data set. So first, we see that these columns, these features or variables, they talk about demographic, lifestyle, or clinical features of the patient, about age, gender, well, diet score, physical activity, the body measure index, body mass index, the blood pressure, cholesterol, family history, so genes, identical history. And then after knowing a bit about the data set, we do the exploration data analysis. This is a kind of summary about the clinical indicators, the age, the body mass index, blood pressure, cholesterol, and so on. You see that is a Gauss bell, so it's a normal distribution. So the clinical indicators are quite stable. This is a summary. Yeah? It's not indicating anything in particular. But you see in the other figure that the lifestyle indicator is a little mess. It adds noise because at the end this is heterogeneous because some of us are optimistic about our healthy routines. No, alcohol. I don't drink alcohol. Just a beer a day. No, or activity. Yeah, I walk every day. No, but well, depend 2 minutes. No, so you can set your in your pulse, no, some of subjective data, but yes, these are variables that we are going also to use. And in this slide, we see the correlation between the variables. A correlation measures how much a variable changes if another does. And at the end, if it's a one-to-one correlation, we will see that one of the two variables, we can delete one of the variables. If we have the birth date and we have the age, it's one-to-one, no? Because I have 43 years. I was born December 82, so we can calculate the age, no? So we'll delete the birth date and we'll stay with the age. In this case, we see that the correlation, sorry, it's not the same, are high when we talk about clinical variables like the heart systolic blood pressure or the cholesterol, and also the age, and moderate maybe with the cholesterol and triglycerids, yeah. But at the end, there is no significant big one-to-one correlations in this data set. So at the end, what we have to analyze in the exploratory data analysis is if we take all the values or we dispose some of them. No, and in conclusion, in this project, I decide to keep all the variables for the training. So this is the figure that you can see. This then we well, is more in detail, but we use a regularization reads that is trying to coach all these variables to give value to the final purpose, and maybe to scalate them or to be homogeneous in terms of calculation. Well, okay, so we go to the models. The machine learning models, we have the typical in the right, the logistic regression, that is a logarithmic algorithm that is one of the first ones in machine learning, and it's like an algorithm with weights. An algorithm like weight is the variable in its. We have different variables, that is the weights of the algorithm, and they are calculated, and they are calculated with the training, and it's easy to understand the result of the algorithm mathematically, if you are a good mathematician, to know how is it calculated. With random forest and light gradient boost machine learning classifier, we have trees. We have a tree, decision tree. So we have a node, then a decision yes, no, no, and another layer of nodes, and then it's a tree of decision. In the case of the random forest, it's only one tree. In the case of gradient boost machine, is multi different trees, and it's more complicated model. So to summarize, these models are already existing in a repository in Hugging Face, and we just do a parameterization of these models. To explain a bit about what do we parameterize in its model, this is the table. We do a pre-processing. At the end, the overall process of cleaning and organizing the raw data, handling missing values, removing noise, formatting, at the end to make it suitable for this machine learning model. We do column transformer. If we have maybe gender that is male and female, we will change into numbers. This is the second step, the encoder. We say 1 for male, for instance, and 0 to female. We do a change from object data to numbers. At the end, the model always works with numbers. So yeah, we do this pre-processing, mapping categories, doing binarization, and then encoding, transforming into numbers as well, the different quality values. We scale. Sometimes a value that has 100 zeros, another is decimal, and at the end we have to scale all the values to make them as important and equal for the training. And the data division is very important. We will have 700,000 lines in total, but we have to split. We will take the 80% of this data set to train our model. We don't touch the 20%, the other 20%, and then after the training, we will evaluate. We train our model with about 500,000 lines, and then we will check with the other 20% of the lines whether we are predicting well or not. So the 80% of the training, the model knows the target value, and the 20% of testing, the model predicts the target value, and we compare with reality to get the metric. And then some hyperparameters. You will see, well, the depth of the tree normally is the number of layers of the tree. Number of estimators is the internal value. Child and number of leaves is also number of the leaves in total. If we put number of leaves 31, we will see that the total number of depth will be 2 to the power of 5, so it will be 5 depth. But we are going to see in the next slide a bit of code, and I will share you also my Visual Studio to see what I did. All right, and then finally we have additional methods like a pipeline to make automatic some of the parameterizing as well. The pipeline will work differently in each of these models. Okay, we are a consulting company, well, and for sure we will see the code in Visual Studio, but first a little summary for those that are not developers, just to show you the typical flow of a train in machine learning. So first of all, we see the X, mayusk, capital letter, for the columns that are the features, the variables, the 24 columns that we are going to use to train the feature matrix. It's very important to know about mathematics. Remember, in the university, matrix, no? 3 dimensions. Well, and then the vector. And then the feature matrix is X, and then the Y is the vector, is the answer. Is only is a vector. And now I'm dotting 2 dimensions. No, Mark, a vector is 2 dimensions, and a feature matrix is 3. Or no, 3 dimensions is a matrix. Mark or any mathematician in the room?
Depends on the model but yeah.
Sometimes I'm dyslexic with this.
Matrix more than 3 dimensions.
yes, more than 3. True. All right. Very good. So, well, in X we will have always the features. In Y we'll have the target value. Then we will have to see what are the categorical columns that are objects that have to be converted, the columns that have to be converted in numbers, and numerical columns that are already numbers, so the machine learning model will understand directly. So we differentiate with this function what are numbers and what we have to change to numbers. Then the preprocessor, here is where we convert the categorical values into numbers. And then in this case we have the light gradient bus model, where we set the parameters, number of estimators, 500 different trees in parallel that will learn about our data set. The learning date is long to explain, but the learning rate is used by the model to calculate in the next iteration the different parameters of the tree, the different parameters of the final model. And if it's very little, the learning rate will go little by little. At the end, is the descent gradient is a mathematics definition of the bottom of the curve. The bottom of the curve is when the curve is changing, the derivative is 0, so we have to find this point. The learning rate helps us to arrive to the points where we get the most optimal parameters for our model. If it's a big learning rate, it will learn very fast, but probably not so accurate in summary. Okay, then the pipeline, we wrap here the preprocessor and the model, and then it gets automatically some of the calculation of before the training, and then the training split, where we talk about if it's 0.2 the test size, we get the 20% of the data set for the next step, that is to test, and then with the 80% we prepare the training. And just a line that says pipeline fit model train, then we will get the parameters updated after 1 hour, 3 days, 10 minutes. It depends on your on your CPUs, GPUs, and your parameters. Okay, so I'm going to show you my my Visual Studio a bit, just to let you know how I work. We have 8 minutes, so I will show this fast. Okay, so well, here I work in 3 different models, no? The logistic regression, the random forest, and the light GBM, 3 different machine learning models. Maybe I can start with the random forest, where you see more about the exploratory data analysis. We are using Jupyter. I encourage you to, if you are learning Python, to use Jupyter notebooks. A Jupyter notebook is a mix of text and code and Python code, and it's very easy to understand. You go from top to the bottom, reading like a document, the Jupyter file. So we see the data set with all the columns, features, or variables, and at the end, the diagnosis diabetes. 1 if you have diabetes, 0 if you don't have. So you see here the latest column, that is the target value. So we have 24 variables and then the target value. We do the exploratory data analysis. We check the type of values, integer, objects, floats. Then the nulls, if we have values that are not giving data, we will delete them. Hiding booleans that we can change to numbers. And then we do like graphic figures of any of these variables: family history diabetes. If you have had in your family diabetes, then you say true. Hypertension, history, cardiovascular problems. No, we see in these figures the different values explored. Or it's like they discover patterns in our data. Yes, the same with in different figures. Python can show you also the layers, data that are out of the normal, that maybe are wrong data or something. We have to study. If somebody said that he does 80 hours per week of sport, maybe his outlier is totally wrong. We will dismiss that. So target value, well, my code is in Spanish. I am studying the master in Spanish, but all the comments. Okay, so here we see like the exploratory data. This is the correlation matrix, and we see the correlation between variables. Age with age, 1 is correlation 1. Alcohol consumption with alcohol consumption is 1. But then you see body mass index with diet score is 0.2. So it's a negative correlation. That means that if you have less body mass index, you will get a better diet score, no? Minus relation until -1, that it will be like a totally inverse correlation. So this matrix gives us very valuable information. Okay, so well, we can go maybe to the logistic regression and we continue. We see, well, the correlations. After the correlation, we declare what are the target values, X and Y, what I explained before. So the train and test. And yes, in the code, well, if you have any question, I may be going fast, but you can stop me, and if you have any question, I can give some details. And well, I also develop the light GBM. At the end, I'm going to the light GBM because at the end, this model was the fastest in training and is very good for big data sets. And at the end, the metrics that it gave were the best. Well, this is the Jupyter notes. I think you have any question, or maybe we come back to the presentation, and at the end I give space for the questions and answers. I will go to back to the presentation. Okay. Now, sorry, I'm sharing. Okay. Okay. So, sorry, no, I stop sharing. Share window. Diabetes prediction. Okay, coming back. So this was the summary. I share a bit the visual. Well, an important point that I want to highlight is we are treating with patients. An important consideration is that we have to prioritize in recall. What is recall? It's an important metric, recall, that is also called sensitivity or true positive rate, and is the ability of the model to find all the positive cases in the dataset. It answers the question of all the actual positive cases that exist, all positive that we have. You have diabetes. We will see. We will say to the patient, "You have diabetes." How many did the model correctly identify? Here we want better our patient to have a false positive and be worried, no? Continue with more tests to confirm or discard the diagnosis, better than dismiss a false negative and then the patient says, okay, I have no diabetes, and forget about further testing or preparation. Then this model is going to be trained for optimizing the recall. That is better for our patient to tell them to be wrong, no, and tell them that they have diabetes, and then encourage him to do more tests. So after doing the training and parameterizing our pipeline to prioritize about recall, we see that the metrics of the light GBM are better, slightly better. Is at the end, these three models are very good for this problem, and we see that the 97% of cases, well, 97% in recall is a very good metric. The other metrics are secondary but also important. Accuracy, the first one, measures the overall percentage of correct predictions, positives or negatives. If we are doing it well, it's 66% of accuracy of our model. It's not a lot, but if we have to prioritize for the recall, it's like this. The precision is also low. The precision measures accuracy of your positive predictions. In a few words, it answers the question of all the cases the model labeled as positive, how many were actually correct? So all the cases model labeled as positive, what are how many were correct? Is different than the recall. The F1 is like an harmonic a harmonic mean of precision and recall, so it's also giving a lot of information. And the ROC-AUC is a curve that explains the ability of the model to give the right answers at a certain threshold. Is longer for explaining. At the end, the light GBM classifier is the winner. In a challenge, what we want to achieve is a good the best model to win the challenge, no? So the best numbers. So we will go with the light GBM classifier. Then we saw before the confusion matrix, confusion, and it's also very important in machine learning. It's a simple way to see the results and summarizes the number of correct and incorrect predictions. This matrix has four sides. These are the true labels. So it's in the data set, we say if we have diabetes or we don't have diabetes. So in this case, this says the true label. No diabetes is these two, and diabetes is these two. Well, So the confusion matrix, I hope not to get confused when I'm explaining it. the x-axis is the predicted labels. So in this side, you see if we have predicted a no diabetes and it was true that it was no diabetes. So in our 140,000 cases, 7,000 were right. We say there is no diabetes, and that's true. It was not in real. And here we see that we have predicted there was diabetes. We have, sorry, in this square, we have predicted that. Do you see my mouse? Sorry.
Yes, we can see it.
Okay, because I say if you are not.
Yes.
Thank you. So we predict there was no diabetes, but actually it was diabetes in 2,700 cases. We were wrong, no? In the right side, the prediction of the diabetes. In 45,000 cases, we predicted there was diabetes, and it was not. No, this is because of recall. We have lots of false positives that actually at the end the patient will not have diabetes, but he will get relaxed later after some more tests. No, and 85,000 cases that we predicted diabetes, and actually at the end the patient had diabetes. No, so in this matrix we see that the numbers of this model, the winner, were better. It's not a big difference, but you see, machine learning, all the models are very mathematically prepared for these kind of problems. Okay. So finally, the conclusions. Well, our gradient boosting model was the best. Was designed to minimize the false negative, maximize the positives, and high sensitivity recall or this metric. And we prefer just to give a false positive and an unnecessary alert to look in a real case of diabetes. And yes, at the end, in the conclusions, the recall is 97%. The most important F1 score is also good, about 80%. More than 80% is always good in machine learning. Around 80% is good. Precision 75 and the curve 73%. So yes, this is the conclusion. At the end, to set a path of improvement, we could do like a feature engineering. Feature engineering within data engineers or data scientists is very important. There are departments in Meta or Amazon just about feature engineering to get new columns or to do the deeper analysis of each column of the data set, each feature, to improve our models. And then also we could check alternative models. This is cutting edge models, but we could have maybe last month a new model. And we could also do a deeper analysis in the false positives in the confusion matrix. What we have been wrong lots of times with the false positives. We maybe we can investigate in this to improve our process, and also maybe we could do external validation, get new data out of these 700,000 patients to improve the model. So well, this was the presentation. It's already more than 36 minutes explaining. Sorry, and thanks a lot for and just questions and answers. Maybe. You haven't understand anything, or it was too much information. I will send you the PDF with the presentation as well, and you can ask me later, or if you have any question.
Jesus, thank you for the presentation. Well, it's been so great to see the end-to-end and the use case. I think it will be great if you can do now with code. Maybe it's not easy, but to take a trained model and to use a new sample that we can make a new input and see the prediction. That we can now use these trained models to fake to, let's say, a new patient, and let's see that in real time we can get predictions of every new patient that we would have. Theoretically, I'm not sure if it's easy for you to do now, just to visualize how easy is now that the model is trained, or maybe you cannot.
I cannot, because the Jupyter, it was compiled from, it will be
You
half
have to
an hour.
rerun it again.
All
no
the Jupyter.
Okay.
Yes.
No problem. But it's so great when you see all the work and finally you have the model, you put the new data of a single patient and you get true or false, or like what the model thinks that this new patient has, if it has diabetes or not. But thank you.
A new line with all the variables features. Yes. I didn't compile it yesterday. I compiled it in Christmas. I did the code in Christmas. All right. I will also share in the community some links. I'm studying in the master, and I will share some of the links that I think is very interesting for the community. And whether you have doubts about the presentation, the models, or the links, I will be very pleased to support you.
It was an amazing presentation, Mark. Really good presentation. The question that remains here is, how do I found your startup when you go for it?
Well, I would like to do a new presentation, because last week I was working in a neural network with images to detect the apneas during the sleep, and I was it's kind of working. I would like to work in that. So the neural networks and so on, it opens lots of possibilities. But yes, thanks, Victor. After you.
Sweet, bro. Keep it on.
Yes. Thanks a lot.
Thank you.
Thank you, Veronica.
Thank you. Good presentation.
Thanks a lot to all of you to be here. And yes, keep in touch.
Super interesting. Thank you, Jesus, and everyone for joining us.